Welcome students to the MOOCs course on Introduction to Fuzzy Set, Arithmetic and Logic. This is lecture number 15. As I said at the end of the last lecture that today what I will start is called extension principle. Proposed by none other than Professor Zadeh. This principle allows us to extend the concept of mapping from crisp sets to fuzzy sets. To keep things simple, we focus on fuzzy sets defined on or intervals on R, that is the real line. So far, we have seen mappings or functions from subsets of R to R. For example, consider f of x is equal to x square. Let a be the interval 1, 3 and let b is equal to f of a, that is b is equal to the set of y such that y is equal to f of x, x belonging to a. Therefore, if a is equal to 1, 3, b is equal to 1, 9 and given any y belonging to b, we can find x such that x is equal to f inverse y, which in our case is root over y. Now, question is how to extend the above for fuzzy sets defined on R. Suppose A is the triangular fuzzy number 1, 2, 3. Then for each y belonging to the interval 1, 9, we need to compute its membership. To B. In the above case, we can do it very simply. Mu b of y is equal to mu a of root y, or in general mu b of y is equal to mu a of f inverse y. Therefore, mu b of 2.25 is equal to mu a of 1.5, which is equal to half when we have a is equal to T f n 1, 2, 3. Similarly, mu b of 4 is equal to mu a of 2 is equal to 1. However, problem comes if f is many to 1. For example, consider a is equal to T f n minus 2, 0, 3, and let f of x is equal to x square. Therefore, f of minus 1 is equal to f of 1 is equal to 1. Question: what is mu b of 1? Note that here b is equal to the interval 0 to 9, because if my input is from the interval minus 2, 0, 3, then the value of x square will lie in the interval 0 to 9. We know that mu b of y is equal to mu a of root y will not work easily in a straightforward way. because f of minus 1 is equal to f of 1 is equal to 1, and mu a of minus 1 is equal to, since we have the TFN minus 2, 0, 3, this is going to be half, and mu a of plus 1 is equal to 2 by 3. This is clear, because if this is minus 2, minus 1, 0, 1, 2 and 3, and at 0 it is 1, therefore, I get this type of picture. Therefore, membership at minus 1 is equal to half, and membership of 1 is equal to 2 by 3. Therefore, what is going to be mu b of 1? It is half or 2 by 3. That is the question. In general, consider a function f on R as follows. And suppose we consider y is like this, therefore, we get at least 5 points x 1, x 2, x 3, x 4 and x 5, such that f of x I is equal to y for all I is equal to 1, 5, and if mu a of x I is not equal to mu a of x j, I not equal to j and belonging to 1, 2, 3 up to 5, then determining mu b of y is not straightforward. Another problem is what is f inverse of y, where f of x 1 is equal to f of x 2 is equal to f of x 5 is equal to y. Thus, we need policies for one, determining f inverse y, and secondly, determining mu b of y, and both of them will need to consider all x1, x2 such that f of xi is equal to y, and also mu a of xi for all I. To take care of such multiple values, we extend the domain and range of f from x to y to p x and p y, where p denotes the power set. To illustrate, let us take a discrete set x is equal to -2, -1, 0, 1, 2, 3. Therefore, P x consists of all possible subsets of x. In particular, let A be contained in P x. 1, A is equal to -2, 1, 0, then f a is equal to 4, 1, 0. If a is equal to -2, +2, -1, +1, then f a is equal to 1, 4, and if a is equal to -1, 0, 1 and 3, then f a is equal to 0, 1, 9. Thus, we get from a subset of x, a subset A of x, a subset B of y, which is equal to, in this case, 0, 1, 4 and 9, such that for all y belonging to B, there exist x belonging to A such that f x is equal to y. Thus, f a is equal to the set of all y such that there exists x belonging to x or x belonging to A such that f x is equal to y. And we can compute f inverse in the following way. F inverse of a set B is equal to the set of all x such that f x is equal to B. Therefore, f inverse of 1 in the above case is minus 1 plus 1, f inverse of 0 is equal to 0, f inverse of 1, 4, 9 is equal to minus 1 plus 1 minus 2 plus 2 and plus 3. The next problem is assignment of fuzzy membership in the event of A is a fuzzy set defined on R. Consider, for example, A is equal to 0 for minus 2 plus half for minus 1 plus 1 for 0 plus 2 by 3 for 1 plus 1 by 3 for 2 plus 0 for 3. Question is, how to obtain mu b of y. The formula is mu b of y is equal to maximum over x mu a x such that f of x is equal to y. Therefore, mu b of 1 is equal to maximum of mu a of 1 and mu a of minus 1 is equal to maximum of 2 by 3 comma half is equal to 2 by 3 and mu b of 4 is equal to maximum of mu a of 2 and mu a of minus 2 is equal to maximum of 1 by 3 comma 0 is equal to 1 by 3. In this way, we can compute the membership of Y to the set B. How to compute inverse? F inverse. Therefore, mu F inverse B of x is equal to mu B of f x. Thus, with respect to the above case, mu F inverse B of 1 is equal to mu B of 1 is equal to maximum of mu A of 1 and mu A of minus 1 is equal to 2 by 3. In a similar way, mu F inverse B of 2 is equal to 1/3, and therefore, mu F inverse B of minus 2 is also 1/3. This is because mu F inverse B of x is equal to mu B of f x, and therefore, mu F inverse B of 2 is equal to mu B of 2 square is equal to mu B of 4, which is equal to maximum of mu A of 2 and mu A of minus 2, which is equal to, as we have calculated, maximum of 1 by 3 comma 0 is equal to 1/3. Therefore, for 2 it is 1/3. In a similar way, mu F inverse B of minus 2 is also mu B of 4, which will in the same way will come out to be 1/3. This allows us to fuzzify a function on crisp sets to a function on fuzzy sets. And this gives us extension principle, which says that any given function f from x to y induces two functions f from f x to f y and f inverse from f y to f x, where f x and f y are set of all possible fuzzy sets on x and y. Question is, what happens if the number of x which produce the same y is infinite? For example, consider f of x is equal to floor of x, where floor denotes the largest integer less than equal to x. Therefore, let a be the interval 0, 5, b is equal to the discrete set 0, 1, 2, 3, 4. Then say all x belonging to 0, 1 will produce the same y, that is 0. Similarly, all x belonging to 2, 3 will produce f of x is equal to 2. Question is, in such cases, how to compute mu b of y, and the formula is mu b of y is equal to supremum over all x belonging to A, such that f of x is equal to y mu a of x. Therefore, mu b of 0 in the above cases supremum over all x belonging to 0, 1 mu a x. Thus, the notion of maximum is now replaced with supremum, as there are infinitely values which produces the same y, we may not be able to identify the maximum, therefore, we need to replace it with supremum. Thus, by extension principle, mu f a of y is equal to supremum over x belonging to a, such that f of x is equal to y mu a of x and mu f inverse b of x is equal to mu b of f x. Let me now give you some simple results. One, f of a is equal to phi implies and implied by a is equal to phi. 2, a1 is contained in a2 implies f of a1 is contained in f of a2. 3, f of union over I a I is equal to union over I f of a I. 4, f of intersection over I a I is equal to is contained in intersection over I f of a I. 5, if B1 is contained in B2 implies f inverse B1 is contained in f inverse B2. 6, f inverse of union over Bi is equal to union over I f inverse of Bi. 7, f inverse of intersection over I Bi is equal to intersection over I f inverse of Bi. 8, A is contained in f inverse of f A, and 9, B contains f of f inverse of B. I leave this as an exercise. These are all very straightforward. If you have understood how you are calculating the membership functions and how you are calculating the inverse, all these are absolutely straightforward to prove. So, before I stop, I give you a an important results which shows that extension principle is strong Cartworthy but not simply Cartworthy. So, let f from x to y be an arbitrary crisp function then for any a belonging to f x, that is A is a fuzzy set defined over x, and for all alpha belonging to 0 1, the following properties of f fuzzified by the extension principle hold. That means, we have taken function f from x to y, we have fuzzified them using extension principle, then we find the following two properties to hold. What are these? One is that alpha plus cut of f of a is equal to f of alpha plus cut of a, and the second property is alpha cut of f of a contains alpha cut of contains f of alpha cut of a. So, this says that we get alpha plus cut of f a through alpha plus cut of a's and applying f on them. Therefore, it is strong Cartworthy, but this containment relationship says that it is not simply Cartworthy. Proof: alpha plus cut of f a is equal to f of alpha plus cut of a. Let us consider y belonging to alpha plus cut of f a. This implies that mu f a of y is greater than alpha. This implies supremum over all x such that f x is equal to y mu a of x is greater than alpha, implies there exists x naught such that f of x naught is equal to y and mu a of x naught is greater than alpha, implies there exists x naught such that f of x naught is equal to y and x naught belongs to alpha plus cutoff a, implies y belongs to f of alpha plus cutoff a. This shows alpha plus cutoff f a is contained in f of alpha plus cutoff a. Conversely, suppose y belongs to f of alpha plus cutoff a, implies there exists x naught such that f of x naught is equal to y and x naught belongs to alpha plus cutoff a, implies there exists x naught such that f of x naught is equal to y and mu a of x naught is greater than alpha, implies supremum over x such that f x is equal to y, mu a of x is greater than alpha, implies mu f a of y is greater than alpha, implies y belongs to alpha plus cutoff f a. So, this proves the first result. Now, let us prove the second result. Alpha cutoff f a contains f of alpha cutoff a. If y belongs to f of alpha cutoff a, implies there exists x naught belonging to alpha cutoff a such that f of x naught is equal to y. Therefore, mu f a of y is equal to supremum over x mu a x, which is greater than equal to mu a of x naught, implies greater than alpha, since x naught greater than equal to alpha, since x naught belongs to alpha cut of a. This shows f of alpha cut of a is contained in alpha cut of f of a, but there may be situation when y belonging to alpha cut of f of a does not imply y belongs to f of alpha cut of a. Consider for example, f of x, say let us call it f of n is equal to 10 when 2 less than equal to n less than equal to 100 is equal to 20 if n is greater than 100, and mu a of n is equal to 1 minus 1 upon n for all n greater than equal to 2. Therefore, mu f a of 10 is equal to maximum over I is equal to 2 to 100, 1 minus 1 upon I is equal to 99 upon 100, because this is maximum when I is maximum, that is 1 minus 1 upon 100. Therefore, it is 99 upon 100, and mu f a of 20 is equal to supremum over n greater than 100 mu a of n is equal to supremum over 1 minus 1 upon n, n greater than 100 is equal to 1. Therefore, one cut of f of a is equal to singleton set 20, but f of one cut of a is equal to 5, since there does not exist any n in A such that mu A of n is equal to 1, because for all of them it is going to be 1 minus 1 upon n. So, it will never get the value 1. Therefore, one cut of A is going to be 5, and therefore, f of that one is going to be 5. On the other hand, because the supremum is 1, one cut of f of A is going to be the singleton set 20. This proves the result. Okay, students, I stop here now. I hope you understood the extension principle. In the next class, I shall work on how extension principle can be used for doing fuzzy arithmetic. Thank you.